Today, in this video, we will talk about binding energy. So we are in the nuclear physics chapter. Please remember that the mass of, let's say, one proton. The mass of one proton can be expressed in kilograms as 1.67262 to the minus 27 kilograms, but it's also 1.007276 atomic units, and it's also 938.27 mega electron volts per square C. Right? We talked about this in class, or we will. Now, similarly, the neutron is 1.67493 to the minus 27 kilograms, 1.008665 atomic units, or 939.57. Same thing. So the thing is, when you compare an atom of carbon 612, remember this is the number of protons, this is the number of nucleons, which means protons plus neutrons. But when you have this together, right, so of course inside you have 6 protons, 2, 3, 4, 5, 6, 6 neutrons, 1, 2, 3, 4, 5, 6. And then, but the atomic mass of all that is exactly 12.00000. This is a definition. Thing is, outside, if you get the 6 protons and the 6 neutrons outside of this, if you manage to put them outside, look at the mass of each one of them, 1.007276, 008665. If you add 6 times this plus 6 times this, you don't get 12. So where is the mass? This is heavier than this. This is lighter. When they live together inside the nucleus, the nucleons, these are the nucleons, remember, protons and neutrons live inside the nucleus. The nucleons are lighter inside than outside. What happens to the mass? Well, this happens to the mass, EmC squared. We talked about this in relativity. You see, the heavier nucleons outside are a result of you needing to give energy to the nucleons here in order to separate them. And that energy becomes mass, right? Energy. Mass is a measurement of energy. So that energy you need to add to bring all the nucleons outside is called the binding energy. And well, the binding energy is actually the difference in mass times the speed of light. So it's mass outside minus mass inside times the speed of light. The mass outside, well, is the mass of all the protons, so number of protons times the mass of a proton, but in this case we're going to put protium because that includes the electron, plus the mass, the number of neutrons times all the mass of the neutrons, minus the mass of the whatever isotope we were dealing with, right? This one includes the electron. That's why here we put protium instead of just the proton mass, right? We don't put this one. We put whatever mass of protium you find on the table in the book. And then here we're going to put the speed of light, which is c squared, right? But remember that the rest energy of one nucleon is, well, the mass of is 1 atomic unit. Let me give you that number. The mass times c squared, but the mass of one atomic unit is 1.660539, and then this times the speed of light is 2.9. I'm using a lot of decimals here. And then this squared. This gives us in mega electron, once you transform the joules into mega electron volts. There you go. This is the atomic, the binding energy for in one atomic unit. So, but we said this is mc squared, right? So this c squared can be defined as 931 mega electron volts over the mass, but the mass is one atomic unit, so we're going to leave it like that. And this is the definition of the speed of light that we write in this equation. And then here you're going to put everything in atomic units, and this is the equation to find the binding energy. Let's do an example. Let's find the binding energy of nickel 60. Nickel 60, the 60 is the isotope, because of course being nickel, it has 28 protons. So according to table 44.2 or 43.2, depending on the book you have in the chapter for nuclear physics, it gives us that the mass for nickel 60 is 59.930786. Okay, atomic unit. So let's find the binding energy. In this case, we have 28 protons, but we're going to take the electron. So we're going to use the mass of protium, which is 1.007825. Be careful, I'm not using the mass. I'm not using this one. This is just the proton. This one includes the electron. It's also in the table in your book. Atomic units plus neutrons, we have 32, 60 minus 28. The neutron, well, that's the 18665. And then we're going to subtract the 59.930786. And this times the 931 we put here. 0.494 mega electron volts per U. So all the U's cancel. Right? And we get the binding energy. This gives us 526.85, let's say, mega electron volts. That's it. That's what keeps the nucleons together. You give this energy, you're going to separate them, and they're going to be heavier. Another quantity that is useful, it's the binding energy per number of nucleon, or A, the atomic mass. In the case of nickel, we divide the binding energy that we just got over 60, and then we get 8.78 mega electron volts per nucleon. Okay. Let's take a look at this graph. What they did in this graph is they repeated the calculation we just did, but for every isotope. Is the binding energy per nucleon. As you saw, we got 8.7, which was the nickel here. And so it's around here. And the thing is, there's one of the nickels that, 28 here, one of the, in between iron and nickel, the energy is maximum. Anything on the left or on the right of this nickel, it has less binding energy per nucleon. Now, when you have a lot of binding energy, that means you're very stable. It takes a lot of energy to destroy, to unpack those nucleons. So you want to be nickel because all the protons and neutrons are cozy in the nucleus. They don't want to go anywhere. Going from the left towards nickel, it's a process called fusion. Actually, I'm going to bring this to the other page. So the stability happens around here. Oops, where's my pen? The stability happens here. And when we go in this path, there are nuclear reactions that involve merging of light nuclei. This is called fusion. There are also nuclear reactions that involve splitting of heavy elements. This is called fission. We will talk about both of them. In fusion, for instance, if you take two hydrogens, one hydrogen and another hydrogen, and you manage to make them touch, there is a huge electron repulsion, but if they touch, they fuse and they become helium, right? And this gives you energy. So when you go from hydrogen towards nickel, right? Could be oxygen towards aluminum, of cobalt towards titanium, but as long as you go in this direction, from light to nickel, this is exoergic. It gives energy away. And the same happens in the other direction. If you have a super heavy element like uranium, 238 with 92 protons, and if it splits, for reasons I will discuss shortly, like for instance, it can give you a helium and then a, what is it you get? Thorium? No. Plutonium? No. Let me see. Yes, it was thorium. Then that also gives you energy. Right? This is, again, fusion and fission. And the reason is because this is more stable. Nickel is where you have more energy per nucleon. It's where the nucleons are, again, more comfortable being together. This is what happens in the sun and in nuclear bombs. Yes, in some bombs, the hydrogen bomb, for instance. This is what happens in nuclear plants and also in some atomic bombs, right? So, and we will discuss this also in class. So you really need to understand how to calculate binding energies for the final exam. I cannot go there. Everything we did here, please make sure you know how to do this.